Hello everyone, this is Dr. Rajesh and I am again with you with my new video lecture, and in this video lecture we will be studying a problem based upon the divergence theorem, and this problem is very important from examination point of view. And the problem is, evaluate this surface integral where S is the surface of the cone, this is the cone above xy plane, and this is the vector field given. So let me first draw the cone. So let us first draw the axis, say this, this, and this. This is the origin, and say this is x-axis, this is y-axis, and this is z-axis. So now cone can be of two types. It can be either of this shape, where this is the vertex, and this is the base. Base is in uh, this vertex is touching the ground, and this will be above the vertex, so this will be the position. So the position could also be something like this one. Base is resting upon the ground, so this could be the position. So now let us see whether it is of this shape or this shape. So if we put z is equal to 0, this implies that 0 is equal to 2 minus root x square plus y square. This implies that 2 is equal to root x square plus y square. This implies that x square plus y square is equal to 2 square. So this implies that when z is equal to 0, and z is 0 in xy plane, so it is a circle. So in xy plane, when z is 0, this may be assumed as a ground. So here uh, in xy plane, when z is equal to 0, so this is a circle. So let me draw the circle. Circle radius is 2, so this is a circle. So this is the circle. Now we will make a cone now, and this will be the cone. So this is the cone, and you can name it this A, B, C. Okay, so this is the cone. And what is the surface area S? This cone without this portion, means the upper portion only. So this is the surface S, which is given, and say lower is S star. So if we see in the surface S, this is not closed because it is without S star, so it is an open surface. And we know that we were willing to use the Gauss divergence theorem on this one because the question was of evaluate. But here there is one problem: this surface S is not a closed surface. So Gauss divergence theorem, sorry to say, but we are not in any position to use Gauss divergence theorem. So we are helpless here. So what can we do? We can apply the Gauss divergence theorem upon the closed surface. So let us say there is surface S double star, which is union of S and S star. So now this S double star is a closed surface because it is closed with the base, and in this S base is missing, it is open. This base if it will not be there, so it will be open. So now it is closed with base S star. So S union S star is a new surface S double star, which is a closed cone, and this is a closed surface. Now this is a closed surface. So we can apply Gauss divergence theorem upon this S double star surface because it is a closed surface. Therefore, applying Gauss divergence theorem upon surface S double star, what will get? Will get S double star del cross F dot n cap over S double star is equal to triple integral divergence of del cross F vector over the volume V. Okay, why it is of this form? Because we know that uh, curl of a vector function is again a vector function. So here it could be like, we may assume it as a phi. So this could be divergence of phi vector. So it is something like, because curl of a vector function is again a vector, so we have applied the divergence theorem, and we could apply the divergence theorem only upon S double star, because this S double star is a closed surface. So what now I am going to do is going to calculate this divergence divergence del cross F. So that this I am going to calculate. Firstly, let me calculate del cross F. So for this I am going to write over here, this will be I cap, j cap, k cap, component of del, curly by curly x, curly by curly y, curly by curly z, component of F. These are the components of F. I am going to write it over here. These are components of F. X minus 2, x3 plus yz minus 3 y square. Now we will be doing I cap, this will be minus 6xy, and this will be minus y minus j cap, this will be minus 3 y square, and this will be 0 plus k cap, this will be 3 x square, and this will be 0. So now further we have to take divergence of this one. So divergence means partially differentiate with respect to x, this with respect to y, and this with respect to z, and then add up. Partial differentiating with respect to x will give minus 6y, and this minus minus is plus. Partial differentiating with respect to y will give plus 6y, and this partially differentiating with respect to z will give 0. So this will cancel out. This implies that del dot del cross f is equal to 0, or this implies that divergence of del cross f is 0. So we have shown that this divergence is 0, and using this in equation number 1 we will get this surface integral over the surface S double star, which is a closed surface, is 0. So we can write it, and you may name it as equation number 1. Name this as equation number 1. From equation 1 we can write S over double star del cross F dot n cap ds is equal to 0. But here we see that this surface S double star is a closed surface consisting of upper surface S, curved surface which is, and the base, circular base. And if I say here S star is a circular base and whose circle is centered at origin and having radius 2. So this is the circle x square plus y square is equal to 2 square. So this is a circle. So now we know that as this S double star composed of two surfaces S and S star, so therefore this surface integral can be written as sum of surface integral over this one and surface integral over this one. So this implies that you may write, since S double star is equal to S union S star, therefore we can write this S double star del cross F ds is equal to sum of two integral del cross F dot n cap ds plus del cross F dot n cap ds. This is over surface say S and this is S star, and this whole we have proved as 0. This we have proved as 0. You may name it as from equation number 2. So this further implies that this S surface integral is equal to, taking this over here, this will be minus del cross F dot n cap ds over the surface S star, where S star is a circle. So this will be the circle. So now again I am going to recall the three projection formulae that we did in the earlier lecture. So I am going to reproduce it over here. So these are the projection formulae that we will be using. Now see, I have again taken figure here. This is the figure of the problem. Here S star is in xy plane. So this ds will be equal to which formula? Xy plane. This formula will be used. Dx, dy, k cap, and normal to this surface. So what will be the normal to this surface? A normal will be in the outward direction. It will not be something like that you will draw it in the inward direction. It will be outward. So normal will be this one. This will be n cap. And see, this is positive k cap, and this is in a negative direction. This is z increasing, this is against it. So this will be n cap is equal to minus k cap. So this will be the normal, and since it is xy plane, so therefore this will be further equal to minus, and what is the value of this del cross f? So once let me write del cross firstly as such, then I will show you the value. And n cap is minus k cap, and ds, in place of ds what will we write? Dx dy, it will be dx dy divided by k cap as such, and the normal is minus k cap. So this is done, and this is surface S star, and this is equal to minus S star. This will be del cross F dot minus k cap dx dy divided by 1. Now del cross F, what is del cross F? You will see over here that this is del cross F. Here if I say this is your del cross F, and we have to take its dot product with minus k cap, so only this component will survive, so it will be minus 3k square. So I will write it over here, it will be minus, this will be minus over S star, and this will be minus 3x square dx dy. This minus minus will be plus, so it will be equal to over S star 3x square dx dy. Now switch to the polar coordinate because it is a circle, and so as to avoid the double integral, one of the limits will be variable, so it is easier to switch to the polar form. Circle is x square plus y square is equal to 4 and is equal to 2 square. So now switching to the polar form, here if we see this whole portion, this whole thing is covered in the circle, this whole thing is covered in the circle. So radius, if I write the polar coordinates as, it will be x is equal to r cos theta, y is equal to r sin theta. So here radius can start from this 0, because this whole is the surface area, not only this perimeter only, no, this whole is the surface area. So this radius starts from 0 and ranging from 2. So I could write the limits of radius as 0 to 2, and the angle theta, say the angle theta, this angle is theta. Okay, and this theta can be from 0 to 2 pi. It can be from 0 to 2 pi. So this theta is from 0 to 2 pi. And we know that dx dy is equal to Jacobian, and this will be dr d theta. And Jacobian, you know, in two dimensional, in polar coordinate, you, when switched from Cartesian to polar, you know it is equal to r dr d theta, because Jacobian in this case is equal to r. So it will become, so I say that this integral over surface S, this is del cross F dot n cap ds is equal to, now put over here, 3 will be outside, this will be double integral, and x will be r cos theta, so this will be r square cos square theta, and this will be r dr d theta. Since here both limits are constant, but here r is written first, so limit of r will be used at first place. Limit of r is from 0 to 2, and theta is from 0 to 2 pi. So this is further equal to 3, 0 to 2 pi, and this will be 0 to 2 r cube cos square theta dr d theta. So this thing is further equal to 3, 0 to 2 pi, this will be r4 by 4 and limit is from 0 to 2, this will be cos square theta d theta is equal to 3, 0 to 2 pi. It will be 2 raised to the power 4 is 16 by 4. This will be cos square theta d theta is equal to, this will be 12, 0 to 2 pi. This is cos square theta d theta. This implies that this is further equal to 12, and now you can write it as 1 plus cos 2 theta divided by 2 d theta 0 to 2 pi. This is equal to 12. This will be theta, and cos theta integration will be sine 2 theta by 2, and 2 is already here, 2 will come outside. This will be, limit is from 0 to 2 pi. So you will put over here, this will be 6, and when you will put the limits, this will be 2 pi. Okay, and when you will put 2 pi over here, sine 4 pi is 0, 0 over here 0, sine 0 0, so this will be the only, and so this is 12 pi. Therefore this integral which was required to determine over surface S is equal to 12 pi. So this is what we are required to determine. If we see over here, this integral we have determined. Okay, and this question is very important from examination point of view, and so that's why I have covered it. So that's all I have from this lecture, and if you have liked the lecture, please like, subscribe, share and comment. This is Dr. Rajesh saying you goodbye, take care, bye bye, and see you soon.